Hi, we will be presenting our project on the CMOS implementation of a flip-flop using Cadence Virtuoso. Digital IC design underpins much of today's technology. We rely on CMOS because it provides a low static power consumption and high density integration density, which are crucial for compact and efficient electronics. So this project focuses on the design of a D flip-flop, which is a key sequential logic that captures and holds data on the rising edge of a clock signal. This entire design, from schematic to simulations, was carried out at the transistor level using CMOS technology in the Cadence Virtuoso. A D flip-flop stores one bit of data and updates it outputs only be on the rising edge of the clock signal. So at the rising clock edges, the D input is transferred to the output Q. Otherwise, the Q stays unchanged. So you can see at the truth table, when the clock rises and the D is 0, the output becomes 0. And if the D is 1, then the Q becomes 1. During any other time, meaning that when the clock is not transitioning, the Q simply holds its previous state. So on the left, you can see the symbols that illustrates this relationship between the D clock and the Q. So to understand how this behavior is implemented, let's look at the internal structure of a D flip-flop. So the circuit is built from two main blocks. First is the gated SR latch, which is made into a D latch by ensuring the reset is always the inverse of the set. This is to avoid any invalid conditions, right? And this makes the Q follow D when enabled. Finally, we add a pulse detector. So this component detects the rising edge of the clock by briefly enabling the delay at that moment using delay, and then direct the clock signal combined in an AND gates. So together, these blocks makes the D flip-flop act edge trigger, even though its internal parts are level sensitive.
Today I will present the structure approach used in designing a CMOS-based flip-flop. The process begins by defining design objective, focusing on power efficiency and speed. The flip-flop was selected due to its reliable edge trigger functionality, making it ideal for synchronous digital circuit. Next, the circuit is designed at the transistor level, ensuring optimal transistor sizing and configuration. Special attention is given to minimizing propagation delay while maintaining low power consumption. Before moving to physical implementation, extensive simulations are conducted to validate functional correctness. This includes transient analysis to assess switching behavior and power dissipation under various input conditions. Once verified, the design transitions into the physical layout phase, ensuring adherence to CMOS design rule. This step involves careful placement of components to optimize performance while maintaining design constraint. Finally, rigorous checks such as design rule check (DLC) and parasitic extraction are conducted. Post-layout simulation confirm that the flip-flop performance remains consistent after fabrication, validating its power and speed targets. Through this structured methodology, the flip-flop design achieves efficiency and scalability, making it suitable for modern high-speed applications. Thank you.
Alright, now so we go to the simulation that we use for this app. Okay, this is the circuit that we do in Cadence for the simulation, which is a transistor level implementation of the DV flip. We use the multiple of PMOS and NMOS resistor that range in a typical flip-flop configuration, and also we use the VDD and VSS as a power rail that connect properly. Then we put the node connection between the wire as a master slave latch structure, and also this present the actual circuit that will be fabricated. So next is the symbolic from the circuit from the previously, that we use the symbol of CLK, D, Q, VDC, and also VSS. This is suitable for the hierarchical design. that proper pin assignments for integration into the larger circuit. This is the test circuit from the schematic editor, which is contain the D flip-flop symbol and also contain clock data and power VDC as the signal sources. We use two pulse source and one VDC, which is we set the VDC with the 1.65 as the voltage for represent the logic high circuit for D flip-flop, which is between 1.65 volt or 5 volt. Next, for the V pulse 1, we use 1.3 volt, period 20 nanosecond, and pulse with 10 nanosecond. And then for the V pulse 2, which is clock, we use the initial value voltage, which is 1.2 volt, period 40 nanosecond, and pulse increase 20 nanosecond.
This simulation result show the timing behavior of a D flip-flop, where the red clock signal provide a regular pulse, and for the green data input change across logic level, and the purple output accurately follows the input on each rising edge, and confirming correct and synchronized D flip-flop operation. This layout were designed in the Cadence layout suite XL, which is display the physical structure of the circuit using various colored layers to represent fabrication material like metal and polysilicon, while ensuring compliance with design rules and maintaining consistency with the schematic for accurate manufacturing. After completing the physical layout in Cadence, I proceed to run the design rule check or DRC check to ensure that the layout complies with all fabrication constraints. The result came back clean with no DRC error detected. This indicates that the design meets all required spacing, width, and layer rules, meaning it is ready to be exported for fabrication and can be confidently manufactured without any physical design issues. After completing the physical layout in Cadence, I proceed to run the design rule check or DRC.
Now, let's discuss the key advantage and disadvantage of the D flip-flop, especially in the context of CMOS design. First, the D flip-flop features a simple design with only a single data input labeled as D. This simplicity makes it easy to implement and understand. It is ideal for synchronized circuit and clock system as it reliably captures and transfers data on the clock edge. Another advantage is it is of cascading. The flip-flops can be connected in series to form registers and counter, which are fundamental building blocks in the digital system. Finally, when implemented with CMOS technology, the flip-flops are efficient, offering low static power consumption, which is crucial for modern power-sensitive applications. However, there are some disadvantages to consider. The flip-flops are sensitive to timing issues, such as setup and hold time violations, which can cause incorrect data to be stored. They also lack built-in asynchronous control, meaning there is no default reset or set functionality unless additional circuitry is added. Compared to simple storage elements, the flip-flop have a higher propagation delay, which can affect the overall speed of the circuit. Lastly, they are not suitable for large memory storage on their own. To handle larger data storage needs, the flip-flop must be integrated into more complex structures. In summary, while the flip-flops are efficient and versatile for synchronized digital design, their limitations in timing sensitivity, lack of asynchronous controls, and scalability must be considered when choosing them for larger or more complex systems. In conclusion, this project has successfully addressed the key objective by thoroughly analyzing and implementing the design. We have demonstrated a clear understanding of the fundamental concepts and applying them effectively to achieve the desired outcomes. The result obtained validate the approach taken and highlight the strengths of the solution. While there are some limitations and areas for future improvement, the overall performance meets the expectation and provides a solid foundation for further development. That's all from our group. Thank you.